Any thoughts on last meetup's material or this week meetup's material if you got a chance to look ahead?
Well, I didn't really get a chance to look ahead. I was actually trying to go over some of the math. I think it's kind of neat, but it's really hard to get through it.
Did you get through the section on inversions?
Inversions? No, I don't know what you're talking about.
You know, we covered that initial material for sorting, like the first
inversions of permutations. Yeah. That actually I was looking at back in I can't even remember the section now. The A and the B about how they relate to how he comes up with a function for that and a generating function.
Oh, okay.
It was actually previous material.
For the instruction counts.
Yeah, well, it was for the instruction counts, but actually what it is like how many times will you when you come across a new maximum as you're traversing a sequence. So what's the expected, what's the variance, what's all of that. Oh, here's people.
All right, so did you anything to share, anything that you found interesting or learned?
Well, I'm just going through it. I mean, I'm nothing other than what's in the book. It's like I don't think I could quite repeat it. But if I go through it enough, I will.
Hey, Miguel, Arthur, how are you?
I'm doing all right.
Okay. It's good to hear.
Same old, same old. How are you?
I'm doing well, thanks. So
I came in the middle of what Michael was talking about there. I came in the middle of what Michael was talking about. What was that? What book were you reading? Or just going back over the chapter? Or?
Going back over the mathematics when we did algorithm M of that big A and that big B. Well, big A.
Yeah. Okay.
He goes on to come up with a relationship, with a recursive formula for computing the probability that you would have as you traverse the sequence from right to left, which is the way to read it, that you would have n times encountered a new maximum. And he comes up with a recursive relationship for that, and then he uses a generating function. And then it comes down to a Stirling number. It's kind of interesting, that's all. I don't know. I think Zartaj was just filling the time. And then he put me on the
spot. No, because for me, I know that I do have a lot of lingering thoughts after the meetup. You know, there's stuff that comes up. There's stuff that, you think about. So, if I assume that if I have those kinds of thoughts that other people would do. So, yeah, I mean, that's all I wanted to know is if anyone, considered the material that we had covered or looked at anything in advance. It's always interesting to know. This one, the main algorithm, which is this Batcher algorithm M merge exchange, is pretty tricky. I've been pondering it like on and off for a few days, and I still don't have the hang of it completely. Like, why does it actually work? But I think I understand the mechanics to some extent. But hopefully, this meetup will make things even more clearer. So yeah, so I think we're all here. We can just start. And the agenda for today is this new section, sorting by exchanging. And the simple example or the simple type of sort that does sorting by exchanging is bubble sort. So we'll look at that. I think it's much easier than probably all the other algorithms that we've seen so far. It's definitely one of the shortest ones. And then Knuth goes over some ways that you could improve on bubble sort. But then he goes to this algorithm that he says that Batcher discovered in the 50s, I think. And it uses the same technique of sorting by exchanging, but it's not quite a bubbling as far as I understand it. So it does use exchanging, but not really bubbling. And then, so there's the algorithm, and we do have the MMIX programs for both of these, the bubble sort and algorithm M, and we look at them briefly during the meetup, and then I'll also do the step through after the end, after we do some exercises. Okay, so our process in general, and we are now on chapter 5 in volume 3. So let's start with that first section, pages 105 through 107. It's 5 minutes. Okay, could somebody explain the table in figure 14? Okay, could somebody explain the workings in figure 14? The table with the columns of numbers.
I'll give it a shot. So in figure 14 here, we've got an array of integers represented down the left-hand column. And that's our sort of starting column of water, let's say, where the bigger elements are lighter and they're going to bubble up. So we start at the very bottom. And we compare 503 with the one right above it, and it's bigger, so it bubbles up. We swap those two elements. We compare 503 to 512. We don't swap them. We compare 512 to 160 to 061 and swap them, and we keep bubbling up 512. Well, actually, it compares less than 908, so we don't do anything there. But then 908 ends up bubbling all the way to the top. And so in pass 2, we've moved down the horizontal line, which is sort of the water level, right? And we said everything above here is in order. The stuff below here, we still need to work on. And we go back to the bottom and we start bubbling things up again. So 87 doesn't need to move up. 503 now does move up another place. And then we get to 512 and we move it up. And we get to 897 and we bump it all the way to the top. We move the water level down and we repeat. And between passes 3 and 4, after we've bubbled 765 to the top in pass 3, it turns out that a whole bunch of elements now are actually in sorted position because they've all been slowly creeping up, bubbling up in the previous passes. And so the water level drops precipitously in pass 4 because all of those elements happen to already be in order. And so this is an optimization that I don't usually see. If I'm just saying like write a naive bubble sort, I wouldn't expect someone to consider this part of the bubble sort algorithm, but Knuth is actually going to like keep track of this water level as a separate variable in his algorithm. And so this allows us to skip a whole bunch of steps. It's not actually going to be n squared time. It's not actually going to be n comparisons in n passes, or even n over 2 comparisons in n passes. He's actually shortening it. So we're sorting this array of, I don't know, what is this going to be, 16 numbers? 16 numbers in only 9 passes, because we're able to drop the water level by more than 1 at a time. So that's kind of neat.
That's great. Any other questions or comments on the workings? We are going to look at the algorithm steps next. So this is more of a general, visual sort of description. Okay, so let's move on. So this will be just the algorithm, that top half of the page, 5 minutes. Arthur stepped away, but I think he went through the reading already. So, oh, okay, he's back. So who can explain the algorithm? Any differences from that initial rough description and the picture?
I could, but I want someone else to.
Could someone else take a shot?
I didn't
Okay.
see. Yeah, it actually helped me to understand what. It wasn't very hard. I mean, it's very straightforward. It's basically the same thing, right? It helped me to see the bound thing being used.
Yeah.
Right. So it is initialized at the the end, the last possible j, and if there is every time there is an exchange, we have a temporal variable t that you keep updating with the j in which the exchange happened, and when the pass is over, then whatever t was becomes bound, which means that the next time when we start the loop again, we are only going to go onto bound, which is as Arthur mentioned. It goes down. Listening to the example, it goes down very quickly, or it could anyway. So it's a cute algorithm.
Did any of you look at the flowchart as well? We've been having these flowcharts. We haven't really paid a lot of attention to them so far. Have you found them useful?
No.
Okay.
Maybe they are. I just haven't found them useful.
Yeah, I would say and we see this also in the algorithm, that probably because of the time in which this was written and the time that Knuth is from, I find that he switches very rapidly from this really high level, but also really imprecise and fuzzy description, and then snaps all the way down to like, let's write an assembly language, and skips out on what I would think of as like formal but high level language. Like even in algorithm B, he's throwing in little parentheticals like, well, I said for j equals up to bound -1, but if bound is 1, then what that actually means is you should just skip to, like, it's full of imprecision, or like the flowcharts that have arrows labeled like 1 less than j less than bound, which you have to sort of infer what does that mean, loop on j from what in what order, and if you want to see the formal definition, you have to deal with the assembly language, which I think is.
Yeah, I wonder if there is like common sense, you would say, back then, that he's assuming that people will have, like, if you say this, obviously you mean this other thing.
I think that common sense is true even today, but I think maybe, and this may be my bias as well, but I think in this sort of writing, I would have less tolerance for assuming common sense. Say, like, we have the tools now to explain things in language that is both high level and precise. But for Knuth, it's very much pick one or the other. We have the high level, but maybe assume some things, and then we have the assume nothing, but you have to read assembler to get at it.
But do you still feel that the algorithm steps lack precision? Is there?
They're certainly less. They're not formal, right? They're not They're like perform step bj or perform step b3 for j equals 1, 2, etc. Bound -1. But then if bound.
Yeah, so I think you do have a point there, but I think the assumption there, maybe this is the common sense that Miguel is referring to. He shows the order in which it's supposed to go. So if he wanted to do something specifically in reverse, then he would say bound -1 down to 1. I've noticed that in a couple of algorithms. But if he just leaves it like that, then that's sort of the default ordering. Is that what you're talking about? Like whether we should be decrementing or incrementing a counter?
Just the use of ... in general, combined here specifically with the use of bound -1 when bound might be, even if it's, if bound is 2, right? He's saying perform step B3 for j equals 1, 2, 1. Right? What does that mean? Right?
You may be right, but I think from a mathematical sort of notational style, that's pretty common. So in mathematical, conventions, when you're dealing with sets or sequences, I would say that is pretty common. It's understood pretty well. So I think that may be what he's relying on, is some experience with that kind of notation. So you're right in that sense.
He is, definitely.
Yeah. Okay. We'll just spend a couple. Go ahead, Michael.
One thing you don't get from the flowchart is how you skip those steps with T. T isn't even mentioned in the flowchart. What you should have is in box B3, I suppose you should say if RJ and RJ plus 1 are swapped, then you set T to J. That needs to be in box B3, and then loop on J is somewhere in there. Instead of J going up by 1, J at the end is assigned to T. And then, so you're missing some details in the flowchart. Otherwise, the flowchart works.
Yeah, the flowchart text in boxes actually matches the sort of short names he's given to the steps in the square brackets in algorithm B. And so I would say that the text is not actually meant as a complete description. The flowchart is sort of
the flowchart is incomplete without the steps above it.
It's a table of contents for the algorithm. But it's a table of contents with some extra arrows, and I'm not sure the arrows are helping that much.
Yeah, I think that's a good way to put it. That the text in the boxes is meant more like a pointer or reference to something in the algorithm, and then you're supposed to get the details from there. But the box as a whole is some visual representation that's somehow related to some other box and allows you to kind of step through in a more visual way. I think that's the intent of the flowcharts. Initially, I was also I found it a little hard sometimes to follow the flowchart, but I've gotten kind of used to them. I like them, but only after I've read the algorithm. So then I kind of know like what he's referring to. I generally don't go to the flowchart first.
In fact, it's just occurred to me, looking at this flowchart, the structure of the algorithm should be a nested loop, right? Where we're doing something until bound goes to 0, and then we're also doing it for j equals 1 up to bound. That's 1. So there's a nested loop structure. But in the flowchart, we've got a figure 8, right? We've got one loop here from B2 to B3, and then from B2 to B4. So that it doesn't look like a nested loop. Is this just because I don't know what a nested loop looks like in flowcharts? Or
no, I think you're right. I think that this is sort of, it's more like a decision diagram. It's sort of like you're at some box and you're going to make a decision based on some state, and it's not like some box that is enclosing another box, or it's sort of like a description of a step or a box, and some of these arrows are nested in that sense, but I think you're right. Like it's not I don't know if there is a standard way to represent nested loops in flowcharts.
Oh, sure there is. You're missing that T. which would be, and if you put the nested loop in there as a flowchart, it would probably have, you'd probably need an extra box.
Well, the T is there implicitly because the box at the bottom, which says B4, named any exchanges, that is referring to T, except he hasn't drawn it out for lack of space, I suppose.
Well, no, if it was any exchanges, that could be a 0 or a 1. That's a Boolean, but T is actually important. It's going to be the next boundary on the loop. So you're going to start, everything goes down, so it's just not
I mean, any exchanges is the name of that step. It's not that it's just that question.
Okay. Well, we agree that it's vague.
Right. It's, and I think this is also like he didn't want to make it probably too verbose because then it would detract from the visual aspect of things. There's too much text, too many things to read. But yeah, let's look at the MMIX supplement and the MMIX code in there. So this is just 3 minutes. Look at it briefly. If you have any questions, we can go over that. We can go over them, but I will be stepping through it in the session after the main session. Okay. Any comments on the MMIX?
Remind me one thing. So in line, for example, in line 06, so I know what it's doing, right? So in line 4, it's storing in KJ the current. So in the current address. I mean the contents of the current of the address of J.
No, in line 4, it's not storing an address. It's
Storing
getting the value of the key.
The value, yeah. Sorry. I meant to say, key B has the address of the bound of bound, right?
That's right.
So LDO is load octa, right?
Yes.
So it's loading into KJ the octa of the address key B with the offset of J. And that, for some reason, that happens to be the key that corresponding to J. And the same happens with the KJJ. You just store in KJJ the following key, right?
Yeah, KJJ would be the next key.
Yeah,
right.
The next key, exactly.
Mm-hmm.
What I want to remember is like these names, are you allowed to just come up with those names, or they're supposed to be initialized somewhere else?
Not sure what you mean. Oh, I see what you're saying. Yeah, this is a snippet. This program.
So this happened before, right? Okay.
Yeah, so you may have noticed if you've looked at the MMS or the MMIX programs that I've actually posted to the GitHub repo. That number one, the declarations or the sort of the name definitions are missing from here. So I added those, and then also there's no main program that calls the function. So yeah, so there is a bit of setup code that's missing. It just focuses on the logic of the actual subroutine or the function.
Makes sense. So one last question.
Mm-hmm.
This is code, so I have my questions are, and we understood the algorithm, right? So the question has to be about the code.
Yeah.
In line 20, and this I didn't look at the actual content to save time. I didn't look into the supplement,
Mm-hmm.
but that's branch if negative, right?
Yes.
So I understand what it's supposed to be doing. It's like if J still is within one unbound, go to B3, right? But why negative? I didn't like how does that is achieved by branch if negative?
Yeah, so that's just the initialization. So often what you'll see is in the actual MMIX implementation, he'll make choices in terms of how to use the counter or how to actually code up the counter. So sometimes the counter is an offset from the beginning of the array. Sometimes the counter is an offset from the end of the array. Sometimes the counter is an address. So depending on how he actually implements the counter and how he initializes it, starts it off, the actual test may be, branch if negative, branch if non-negative, branch if positive. So it just depends. You have to look at the entire setup for the loop. And again, if you look at, you can look at the GitHub repo because I've posted the MMIX program for this particular algorithm already. The link is there on the Meetup page, and I'll paste it in just a second over here as well. But yeah, so then I've added those comments as well. Like, what is the counter actually representing? Is it an address? Is it an offset? Is it scaled by? Usually, it's even scaled by octabytes, so it gets a little more complicated. Yeah. Did that answer your question?
I mean, sorry, but the answer I heard from you was you will find out in the debugger.
Yeah, you will find out in the debugger, but if you want an answer right now,
I mean,
we
I
can.
honestly I missed we stopped talking when I still were like four lines to look at. So I guess that's what you understood. That you said that line 20, we hit it the first time, and then we won't hit it anymore until we get there again. Like, yeah. So we have to wait until the debugger, I guess, to see clearly.
Okay. All right. So let us move on.
Well, I think there is actually maybe one more thing to say about this, which is relevant to the that you were talking about with the changes that are made for the assembly code. If you look at the English paragraph above it, it mentions that the two parameters that are coming in are key and n, where key is the memory location of k sub 1, which is actually interesting, right? Because that means he's using zero-based indexing in the actual algorithm. So for lines that say like bound gets n, really we expect that to be like bound gets n minus 1 in the code, because we're not indexing into the key array with 1, 2, 3, 4, right? Where key is already the memory location of k sub 1. So we're indexing into key with 0, 8, 16.
Yes.
Right? Not 8, 16.
Yes.
20. Yeah.
Yes, that's right. So the algorithms and Knuth's convention is usually to start an array at index 1. Sometimes it's not really critical to the algorithm. You could just as well start from 0. But in the MMIX code, it's pretty much always 0-based indexes.
Right. And so that means the comments along in the right-hand column are not always useful.
There's often an off by 1, so they're more representative of the algorithm. So you can, sort of match up the algorithm and the code.
Right.
But yeah, you have to realize that the code, in terms of the implementation, is making certain choices that could be a little different. But the intent and sort of the state of the program should be the same. As far as the
Right.
comment and the actual line of MMIX code goes.
The right-hand column is quotes from the algorithm in the book, but that does mean that, for example, on line 20, when it says 1 less than or equal to j less than bound, but the code actually says branch if negative, that's because there's an off by 1, and so really what it's doing is saying if 0 less than or equal to j, fall through, otherwise, go back up to here. But the comment says 1 less than or equal to j because it's using 1-based indexing in the comments, but 0-based indexing in the code. So that's where the negative comes from.
Does that help, Miguel? If that was related to your question? Miguel, you're muted.
Sorry, yeah, so we can continue.
Okay, cool. All right, let's move on to, there's a little bit of analysis. There's a little piece in the supplement on the very next page, and then there's a couple of pages in TAOCP itself. But, just spend a couple of minutes, and if you see anything noteworthy, then we'll discuss it. Okay. So responding to Arthur's comment about the pop instruction at the end, I guess you're asking because he sometimes has a pop in the code that's shown and sometimes it doesn't. Is that the reason?
Well, I kind of forget what pop does, but
Oh, pop is just a return.
Oh, so it also is a control flow change. It's not just changing the
Yes.
the local registers. Okay.
Yes. Yeah, it's a simple return. So 0 means it's not returning anything. It's void.
Okay.
But yeah, I thought maybe you'd notice that some of the MMIX snippets don't have a pop at the end of the subroutine. And I guess that's just kind of assumed, but where it's important to the logic, then I think he does include it. And in this case, yeah, it is the branch for the test if there were any exchanges. So,
Right.
anything about
Actually, the pop does change your registers around. Remember, he has that thing like when you push and reserve X number of registers, where X could be any number between 0 and I guess all the way up to 255, maybe not 255, but any number of registers, and then those registers get saved.
I totally remember the register stack business, but here it's a pop 0. So that is a no-op in that sense, right? But it's the control flow aspect that I was forgetting.
Oh, pop 0 would still put you back at the instruction after push.
Okay.
Like a return. But it does more than return, because when you push, you reserve a certain number of registers, and they have to be starting at 0. So
when you pop, you specify a number of registers to unreserve, and here we're specifying 0.
Yeah, I don't know about that.
Yeah, pop. So the 2 zeros. The first 0 is basically it will tell you what is the first register that has the return value in it. But when it's 0, that means there's no return value, because when there's a call to a subroutine and then there's a stack that is being updated with the saved registers not being accessible anymore, there's one register that's in between that's sort of marking, the separation, the partition. So one register is going to be used for that. And in this case, it's 0. So that 0, when you say pop 0, that means that there's no return. There's no register that has the first return value. And the second 0 is saying what is the offset after the push instruction to which control should return. So that 0 is saying, yeah, just go to the instruction right after the push check. Okay, anything about the analysis?
I had that one other comment that I put in the chat. He's got one sentence in there that I don't really understand what he's getting at. I'm not sure I'm expected to understand that sentence exactly. It seems like sort of an idea, just spitballing here, but I'm not really sure what he means. Or
so,
like, I guess you have your array, and if you want to get this element over here, you could actually swap it over there and shift everything else down, or you could just increase the size of your array by 1, copy it over there, and then stop looking at element 0 of your array, I guess is what he's saying.
Okay, so this, you're referring to something, you've actually read ahead. So you're not supposed to read that part yet. That's part of the next section, the refinements of the bubble sort. But we'll get to it in the next slide.
So I was trying to understand CJ. CJ is the biggest of the insertion. I mean, I don't understand what the I thing, where the I comes from, basically. So
the definition of CJ is pretty straightforward. He says CJ is the value of bound -1 at the beginning of past J. But then he expresses it in terms of the inversion table, and I think that's where it gets a little complicated.
Exactly. So
I think
what it's supposed to be, but how do you get there? Is that what
in equation 5, right?
Yeah.
Yeah. So this is a math notation trivia bit here. We're saying CJ is the maximum of this set, and the set consists of every b sub I plus I for every I such that b sub I is greater than or equal to j minus 1. So
I was reading that it was, because in programming languages like Scala, the pipe means is this or the other.
Yeah.
Oh no, yeah. So Arthur is absolutely right. That's set notation. You read it as such that.
Such that, right?
Yeah.
In mathematics, that's such that, but the B's are the coefficients of the inversion table.
Mm-hmm.
And what he points out, I don't know how it comes to that, but what he points out is that you start off with an inversion table that represents your unsorted array, and every pass of the bubble sort algorithm, all of the coefficients of the inversion table decrease by 1, except for the zeros, which stay 0. So if you want to count the number of steps that you need, it would be the biggest element in the inversion table, whatever that is. In this case, I guess it's 8. So there's 8 steps, 8 passes of the bubble sort algorithm, and yeah. So when what he's saying there is to get the bound at the end of a certain pass, you would look at the number of elements. You would look at the index. What is it? The index or the number of elements?
It's the value of the element plus its index for every number in the inversion table whose value is greater than or equal to the current pass number. And you take that maximum and you subtract the current pass number. But the thing Miguel was missing, though, was just that the pipe means for all I such that.
Mm-hmm.
Right? It's a introduction of the name I. Right? I didn't mean anything before. Whereas J here means defined in the sentence beforehand. That I just came out of nowhere, brought into existence by this pipe.
Yeah, what did you think of using the inversion table for the analysis? I thought that was really interesting, and I think once you kind of get used to it, then it would be very, very useful. But I think in the beginning, it can be a little confusing to switch back and forth between, because permutations come a little more naturally. I think you're more generally, I'm more accustomed to them, and you're not accustomed to thinking in terms of inversions. But this analysis was very interesting that way.
Here's a question that's going to send us down a rabbit hole.
Mm-hmm.
Have we seen an algorithm to compute the inversion table of a permutation? And how efficient is that algorithm?
Okay, so in the very, I think in volume 1, maybe, or no, he doesn't introduce inversions till this volume. But I do remember in volume 1, there is a whole section on programming for permutations. But I don't think inversions are covered there. So maybe they are in this volume somewhere else, but probably in some exercise, there is something like this. So it would be interesting if anyone gets a chance to follow up on Arthur's question.
I don't think it would be very hard to do. Maybe in MMIX it would be.
Well, I mean, we've seen the definition. Like, it's very easy to do in quadratic time. I was just wondering if there was going to be some efficient method of, given a large permutation, write out its inversion table in a program in an efficient way.
Yeah, I think it's a very valid question, and my feeling is that it'll be here somewhere. I haven't seen it, but I have a feeling it'll be here somewhere. And then there is, of course, in volume 4A, I think, is like all sorts of permutation-related topics and algorithms. So maybe it's in there. So okay, so now we will go on to the next page, 109 and 110, and you'll see what Arthur was talking about in his chat comment. And this is, again, just 3 minutes on this. Okay, let's take a break till about 3:15, and when we come back, we'll discuss what we just read. Okay, we're back.
And we're back.
So I guess two things here. First, could somebody explain the cocktail shaker short diagram? And then we can look at Arthur's comment. Maybe he's already figured it out by now.
Okay, let me give it a try.
Okay.
So what I understood, I mean, I honestly didn't spend too much time thinking about it, but it seems to me that the whole point is you do a pass left to right, make all the exchanges that you need. Then if you do a pass right to left, and when you cross another some element that did not change anymore, that's the last, its final destination. That's what I got. I wasn't very clear why that's true, but that at some intuitive level, it seems like okay. So yeah.
So one way that this evolves out of the bubble sort is he mentions that if you go back and look at figure 14 again, which was the straight bubble sort, the very first comparison that we do is bubbling up 503, right? Swapping it with 087, and then 503 doesn't move any further. And so on pass 2, the very first comparison we do is again comparing those exact same two elements, 087 and 503, which we already did that comparison once, and now we're just doing it again. And so as the big elements bubble up, the small ones are also they're coming down. And you see that by pass 3 in figure 14, or at the end of pass 3, we've actually got 061 at the bottom and 087 second from the bottom. And 170 is pretty close to its final answer, but as we're making an air gap at the top and lowering this water level, we're also putting the stones at the bottom very slowly. Or there's a tendency for the stones to end up at the bottom, but we're not consciously doing it. We're not making an effort to do it, but it's happening, and we're not using that fact. We keep going back to the bottom and going through a bunch of stones before we get to the bubbles that need to continue going up. And so what the cocktail shaker sort is doing is saying, let's recognize that and exploit it. And we'll actually keep track of two things, the water level and the stone level, and we'll go back and forth and try to make them both increase very quickly, as quickly as possible.
Yeah, that sounds good to me.
And then when they meet, it's completely sorted.
Yeah, so now we have those two horizontal bars. Like going back and forth. Okay, so Arthur, did you figure out your question or?
Not completely. No, the part I didn't follow about the shifting the origin of indexing. I mean, I have a vague idea of what I think he probably means, which is maybe all he expects you to get out of it, but I'm not really sure how you turn that into an algorithm.
I think what he means by that is that if you look at, let's say, if you look at the first pass there, and look at what happened on the first pass, most of the elements shifted down by 1. So if you look at the ones that shifted down by 1. And if you think about that, that's one read and one write for each one of those shifts. And he's saying, well, what if instead of shifting them down, we set that we just move the base of the array up by 1? So that would mean that to do the first pass, what we're going to do is we're going to take that 087 and keep it in a register. And now we're going to say that the first element of the array is that, oh gosh, I've lost my page now. What is the next one?
110 or page number, or?
No,
Okay.
yeah. Okay, yeah. Yeah, okay. Okay, so we're going to take that 503 and keep it in an array, or in a register. And now we're going to say that the array starts from that 087 and goes up to 1 after the 703. We're going to move the array up by 1. And then we don't have to move the 087. We compare it and we say our 503 in the register is still bigger. And then when we get to the 512, we say, oh yeah, the 512 is bigger. So we pull the 512 into our register and we put the 503 in the second spot of the array, of the new array.
Right. Okay, so this is something that really only works with the cocktail shaker sort, because
it's not a cocktail shaker sort, but it's this sort with, you're going to need.
What I'm saying is, this is something that only works with the cocktail shaker sort, because the cocktail shaker sort shifts everything up by 1 and then down by 1, and then up by 1 and then down by 1. If you tried to do this,
no, actually,
up and up, and then you'd need more space.
No, you just
trick.
You need more space.
You only need one more space, though.
But what he was saying there, I think, is that you just need extra space at the so that you can keep shifting the array up by 1 on each pass.
Why?
But with the shaker, you don't. You shift it up by 1 and down by 1, up by 1 and down.
Okay. But what I'm saying is that the idea of shifting the array applies to just the bubble sort. Not if you apply the idea of shifting the array to the cocktail shaker sort, then you're right. You move it up by 1, move it down by 1, move it up by 1, move it down by 1. That's even better. But I think the way I read it anyway was that he was just improving the bubble sort, and he was saying that by shifting the array by 1 on each pass, which means that you need to have extra space at the top there for however many passes you're going to have.
Which is n in the worst case. Yes.
Is it? Is it? Yeah, I guess it must be.
Yeah.
But you're right. You're absolutely right that if you did that array shifting for the cocktail shaker sort, you'd probably save a lot of memory reads and writes.
Yeah, so my take was also like this applies to both bubble and cocktail shaker. And
it applies much better to the cocktail shaker sort, though.
Yeah, but the idea would be, as far as I understand it, is to eliminate those series of one-step exchanges. So whenever you come across that, you're just sort of optimizing the need to have those one-step. Like when 908 moved up a lot, right? In the first pass in figure 14. So we didn't really need to do that.
Yeah, 908 moved from position 5 all the way up to position 16, and everything in between moved down by 1.
Yeah.
Instead of moving those however many that are, like 10 elements down by 1, which is 10 reads and 10 writes, if you shifted the array position by 1, you save those 10 reads and writes.
That was my understanding.
That's the insight of it. And if you do it on a cocktail shaker sort, then you don't need a lot of extra memory. You just need one extra cell at each end. I'm not even sure you would need that, because if you just had that, you could keep those in a
yeah, I don't think you need extra memory as far as my sort of vague idea of how it would be implemented. I don't think you need it. Just play with offsets. Okay. So now we come to.
Well, actually, yeah, you do need extra memory, because let's say here's the case. Let's say you had the array was perfectly in order, except the first item was the very biggest item. Then you're going to do it in one pass. You're going to shift the array up 1, and where are you going to put that item in the end? You need a blank cell at the end. You need 2 extra cells. You need if you're on the shaker sort, you need an extra cell on both ends. You need one extra memory position on both ends, and you don't know where the array is going to end up.
Yeah,
it may end up. Yep.
Okay, so this one is
Okay, maybe
basically the end of our reading for today. And so this is going to cover the introduction to Batcher's parallel method, and then the algorithm itself, along with the little bit of analysis that's after the algorithm. There's also a table one with a similar operational diagram on page 112. So we'll spend about 7 minutes on this. So I know this will be a lot of material for 7 minutes, but if somebody can give, like a CNN breaking news short version of what the idea is here. Just whatever you've got out of it so far.
So this is vaguely reminiscent of the like P-ordered and H-ordered stuff that we were talking about a couple weeks ago, which I have now completely forgotten the context of that. But I was saying, if you only look at every H element, and if that's sorted for all of the H different sequences of stride H, and then you again sort, by. But where was this coming up? You know what I'm talking about, right?
So that was shell sort, where we improved on insertion sort by saying, instead of a step 1, let's say that we have a step H, so that we can compare these things that are further apart and somehow maybe make them jump, to the right position in the sorted array earlier.
Yeah. So
but this is not exactly the stride, right? Because it goes all the way to the, not exactly the end, but so in the first step, it compares Ri plus 1 and Ri plus D plus 1. And D is this very, like, almost to the end number that is related to power of 2.
Miguel, instead of the mechanics right now, could you tell us what your sense is of?
I don't sense anything. I try to understand the mechanics so I can understand what it's supposed to do.
Right. So that's what I'm trying to get at. If anyone got any sense,
I understand it better through mechanics. So
and then we can go into the details.
Well, I get 2 things out of it.
Mm-hmm.
The first is that each pass. Well, the first thing that I get out of it is that you could really do this in parallel, because each pass is only comparing. Each of the comparisons doesn't serve as an input to a future comparison in the pass. So, like on the first pass, you're comparing 0 and 8. And then that's whatever they are. That's all you're doing. You're just comparing, and nothing else is touching 0 and 8. You do 1 and 9, 2 and 10. So it's really parallel, because it doesn't matter what order you do. 0, 8, 1, 9, 0 compared with 8, 1 compared with 9, 2 compared with 10. All of those can be done in parallel, and if one finishes first, it's not going to matter to the rest of the algorithm.
So that is probably the coolest takeaway of this algorithm from what I've been reading about over the last few days. But how is it supposed to work? Like, what is the approach that it's taking? The parallel aspect is very, very cool, but even before that, like, why is it even, like, how is it even sorting?
So I have not really understood algorithm M, but by looking at table 1, I can see that basically what we're doing is starting P at very large power 2, in this case 8, and we're 8 ordering the vector. So this is now 8 ordered after the first step. And then the next thing we're going to do, we divide P by 2, so now P is 4, and we're going to 4 order it. That takes 2 steps. And then we're going to divide P by 2 again, we're going to 2 order by doing comparisons of stride 2, and that's going to take us 3 steps. And then finally, we're going to 1 order it, and that's going to take us 4 steps. So at each phase of the algorithm, we're dividing P by 2, and then we're taking 1 more step than we took last time. So this is, in total, it's going to take log n So take some number of steps that we're comparing half of the element to the other half, basically.
Oh.
Okay, so now this is a good segue to the table. So let's look at the table and explain. I mean, Arthur's given us a good start on how to interpret that table. This is on page 112, table 1. But if somebody could go through just the mechanics of like each row, could you just explain whatever you're understanding it? It doesn't have to be correct. If you could relate the parameters to what we're seeing happening in the array.
Well, I can tell you that P starts at 8, and we divide this into 4 phases, right? P equals 8, P equals 4, P equals 2, and then P equals 1. And in each of those phases, we start Q back up at 8, and we drop Q until it hits P. So we do 8 and 8, and then we do with P equals 4, we do Q equals 8, Q equals 4, and then they're equal, so we go on. So we drop P again, now it's 2, we start Q back up at 8, we go 8, 4, 2, we drop P down to 1, we do 8, 4, 2, 1.
Okay, so P starts out at some maximal power of 2 based on the size of the array.
Yep.
And then it's being adjusted as decreasing powers of 2. And so there's a loop over that P. And then there's a loop over Q, which always starts out again and again at that maximal power of 2, and then it goes down to whatever P is. What are R and D?
Those I don't know.
D is just the step size.
Okay.
So D is this, like if D is 8, then we're comparing element 0 with element 8 and element 1 with element 9. So we're comparing I with I plus D. And that's the only kind of comparison that we're doing. But
how is D related to P and Q?
Well,
you're right, D is the step size, but how is it affected by P and Q?
Well, in each phase where P is a certain value, we're trying to P order the array, and D then needs to run through and compare every pair of elements at that stride that hasn't already been compared in a previous step. So we've already, in step 1, we compared everything at stride 8. And so in steps 2 and 3, we need to compare all of the different possible things, all of the pairs of elements that are separated by a multiple of 4, right? But we don't need to do the ones that are separated by 8 because we've already done them in the previous step. But we need to do the ones separated by, by this amount of 4 and this amount of 4 and this amount. I don't have the words for this, but we do all the 4s. And then now we've done all the 8s and the 4s. And so in phase 3, when P equals 2, now we just need to compare, now we're trying to 2-order the array. And so we've already done all the 8s and 4s, and we just need to do the 2s and the 6s. Right? And then in the final phase, when p equals 1, and we're trying to 1-order the array, we've already done all the 8s, 4s, 2s, and 6s, and the only things we have left to do are the 1s, 3s, and 7s, but not 5s. Why not 5s?
Yeah, that doesn't make sense. The 6 doesn't even make sense. The 6 doesn't even make sense because if you're going to 2-order it, it's already going to be 6-ordered. But I mean, by the way you explained it, the 6 doesn't make sense. I'm not arguing that
the doing the 6 is part of the 2-ordering yet. It's not 2-ordered yet. It's only 4-ordered so far.
It's only 4-ordered, and then the first one you're doing a step of 2 that's going to get some of your 2-ordering in, and then on that second part of you're doing a step size of 6. Why? Why is that needed? I mean, intuitively, it's needed because on your 2-ordering, some of the items that are in your 2-ordering may need to move a long distance, and if you just did it by 2s, and you would need a lot of steps. So that 6 gets things that are way out of order in the 2-ordering to get to the other side of the array. But
what is R? What is R?
What is R?
I was going to ask that. Have you any of you have seen what is R used for? And I know how they define it with this bitwise, but I haven't seen it used anywhere yet.
So R is used in step M3.
So I see there that R is equals to I bitwise P, and
yeah, but again, the sentence starts with for all. So this time the for all is written out, but you missed it.
Wait, what?
I such that
I see.
and I and P is R.
Such that. Oh, got them. Okay.
Yeah. So M3 has 2 conditions.
So yeah, I got it. So as long as I is between n 0 and n minus d, and happens to be I bitwise p equals r, and r is then was initialized to 0 first, and in in n5 it becomes p. So weird. Wow.
So M3 has those 2 conditions. One is simply just saying, which elements are possible to compare with a step size of d. That's all it's saying, that I needs to be between 0 and n minus d. The second one, this I and bitwise and with p equals r, this is very mysterious. But the way I've sort of understood it is that p is always going to be a power of 2.
Mm-hmm.
And I is just some index, right? So when you're ANDing it with a power of 2, you're essentially checking if I is in a certain range. So for example, if the power of 2 is 2, right? So if p is 4, then you're checking if bit 2 is on in the index of that entry, right? And so that will be on for 4, and then 5, and then 6, and then 7, right? And then it'll turn off that bit corresponding to that power of 2, which is p. And so then those entries are not going to be compared. So initially you start out with this whole range, like the first half, some initial portion of the array where comparisons are possible with something that's d distance away. But within that range, there are smaller sub-ranges that are enabled for comparison. And that's what the I and P equals R is doing. It's checking if that bit is on, if that entry belongs to a certain interval, and that those intervals are going to change in every pass. And that determination is based on R, which takes on a value based on P. Well, actually, it is just P. Usually, it's just P, like except for the very first time when it's 0.
R is 0, and then R becomes P for the rest of that phase.
Yeah, yeah. So it gets really tricky, but once you understand at least how the parameters are being used, then you can kind of see the table is selecting or showing how different ranges of powers of that lie between powers of 2 are being selected in different phases. The way that I've understood it so far, and actually Knuth also explains it this way, that there's 2 phases really. The first phase is the sort phase. The second phase is a merge phase. So the sort phase, or actually it's better to understand it with the merge phase. The merge phase is when P is 1. So if you look at that table, you look at the last 4 rows, of the parameter values, that's the merge phase. So anything above that was the sort phase. When the sort phase ends, that is when P becomes 1 for the first time, at that point, you've got all those orderings. You've got the 8 ordering, you've got the 4 ordering, you've got the 2 ordering, you've got the 6 ordering, but that's it. It goes down to 2. Obviously, if it's 1 ordered, then it would be completely ordered. So once you've got all those orderings, essentially when it's 2 ordered, then you are left with 2 arrays that separately are ordered, right? All the odd indexed entries are ordered, all the even indexed entries are ordered. That's really all you care about, is once you hit 2 ordered, you don't care about the 8 ordering or the 6 ordering. That's how you got there. And then the last 4 sets of values for the parameters, that's the merge phase. And it's merging the odd and the even sub-arrays into a final 1 ordered array at the very end of the table.
Right.
So what's really interesting is this R, right? How it actually enables within a certain pass, even though you've got a whole bunch of entries that you can, compare for some deordering, they don't actually get compared. Only a very select number of subsets of that entire range it is enabled for comparison. So those are the 2 checks. The first check is this particular entry at I enabled for comparison? And that check is done with the I and P equals R condition. Then if it's enabled, then you check, can we actually make an exchange here? That's just the straightforward comparison of the keys. So now why it actually works, that I don't really have a good grip on. I mean, I've looked at the diagram that he shows after the algorithm, after the table, but don't quite get it yet. So does that help?
Do we want to talk at all about the lattice diagram business?
Yeah, if you have any thoughts on it, that would be great. Yeah.
I don't, other than that, well, I understand what he's doing geometrically, but my eyes kind of glaze over at the previous paragraph, which explains how this is relevant to this algorithm.
Yeah, I think it requires a little more deeper understanding of the parameters and the way that path is being followed. But yeah, and it's this R, the value of R that is selected, as a power of 2 with essentially, P, that is kind of making it parallel in that sense, as far as I understand it. That parallelization comes from this fact that, you've got these comparisons being made that are independent of that position, and you can do them independent of the value, and you can do them separately.
So for each pass, every element in the array is either not compared with anything, it just stays where it is, or it's compared with only one other element in the array that is d distance apart. It's either every element in the array is going to either not be compared, or it's going to be compared with I plus d, or it's going to be compared with I minus d.
Michael,
one thing about R is that when R is 4, the first 4 elements of the array are not compared. And when R is 0, the first elements are compared. I think when R is 0, every element is compared.
When R is 0...
When R is 0, every element is compared with something else. When R is 4, the first 4 elements are not compared. Is that true? I think
no,
it is.
I don't think that's true. I think that's just a case of this particular set of values.
I believe that is true as long as you have a power of 2 sized array that you're sorting. I mean, if we had one extra element in this array, then obviously with R equals 0, you couldn't possibly compare every pair of elements because you'd have one left over. But other than that, I think your intuition is correct.
Okay, then when you have an element that doesn't fit into a power of 2, your mapping would give, like, for instance, if you had, this is 16 elements, if you had a 17th element, and on that first row you have 17 would be compared with 17 plus d, which would be 17, which would be 25. But 25 isn't there, so it isn't compared.
Right. And in fact, if we had 17 elements, we would have an additional step, I believe, at the beginning with p equals 16, in which we only compare elements 0 and 16.
Okay.
And then we go on to the rest of the...
Okay.
Right.
Yeah, with 17, you would start p at 16.
Start p at 16, q at 16, d at 16. And there'd only be one comparison to do.
Right. And then you would have 2 steps for the 8.
And then, would the next step be 8808? Or would
it would be 81608.
81608, okay.
And then 8884. No, 8888. So it would be
yeah. So Q just goes down to P, whatever that is, and then P, the outermost loop is over P, and that's going down by 1 power of 2 every time.
I think it would be, those would be the first 3 steps. I think. Not that it matters.
Yeah, that seems right.
It's magic that it works.
Yeah, yeah, it is.
But one thing about it is that every element is only compared with at most one other element. You should be able to tell by the index of the element which element it's going to be compared with, or no element at all, given that you're on a particular step. Given the PQRND, you should be able to figure that out.
So Michael, if you were to parallelize this, how would you do it?
Well, the first step would be to decide how many parallel threads I can work with. Like if I had 4 cores in my CPU, then that would be 4. And then what I would want to do is I would want to have each one of those. I would want to divide up all of the comparisons. There's 8 comparisons in that first step. I would want to divide it among 4 threads.
And how would that division happen? How would you map for each pass? How would you map the comparisons? So, for example, here.
Well, there's probably too much overhead to save much, but once you've like let's say you had 1,000 elements, okay, and you had 4 cores. That's what you should think of. 1,000 would be the power of 2 would be 1,024. So your step would be 512, and you would have 512 jobs. Is that right? 512 jobs. Yeah, something like that.
I mean,
let's say you had 1,024, just to make it even. Then you have 512 comparisons to do, and you have 4 cores. So you're gonna let the first core do the first 128 comparisons, and the next core starts at 128 and compares 128 plus 512, 129 plus 512, and it just does it's 128, and every core does 128. And when the 4 cores are done, you've got that first step done. It's too much overhead to do. In an array this small to do it parallel. That's why I think most parallel sort algorithms, if the algorithm has parallel sort at all, it says, well, if I've got less than 20 elements to sort, I'm not going to bother parallelizing it, or with some number, whatever the number should be.
Yeah, I know that sort algorithms in practice also will say things like, well, if I only have 20 elements, I'm not even going to do quicksort, right? Like, just do a straight insertion sort. It's 2 nested loops. It's super fast. And it's only when you get up to the larger number of elements that factor of log n starts to matter.
Yeah, but the trick is to the trick is that you're not, if you're comparing 512, if you have 512 comparisons to do, you're not going to divide it up into 512 threads. That's much overhead. Like 4 or 6 or 8 threads, depending on your CPU. If you have a lot of cores, then you could use more. I don't think you'd save anything going much beyond the number of cores that you have.
And in real life, you'd have to also worry about, cache interactions and like, can I be operating on element n when some other core wants element n plus 1? Probably not. And all sorts of practical concerns here.
Which is why my intuition would be to do, you have 512 jobs. My intuition would be that the first thread does 1 through 128, and the next one does 129 through, so that you would kind of hopefully avoid that. But you're right.
And that works for the first step, but then in the later steps, it
still works.
And this is all assuming that comparison is the expensive thing that needs parallelization anyway. I mean, comparison is probably super cheap if it's just comparing integers. And if it's comparing strings, well, the strings aren't even stored there, right? They're stored somewhere completely different in memory, and who knows what that's next to. And so it's a mess.
Probably works even better for strings than it does for an array of integers.
Well, so with strings, you would save more by parallelizing because your comparisons would actually be expensive. It's worth doing them in parallel. but they're also more complicated and involve touching more memory. So
Yep.
yeah, that's where I would think more about cache effects.
Okay, so we are a little past 4, and I guess I will just start the step through, and we can look at bubble sort for a bit, and then we look at this algorithm M.